Okay, it's time to start. I sent you guys an email. Please look at it if you haven't already. This week, the schedule's a bit disrupted. I have a mandatory university assignment later in the week. Once a year, I'm responsible for reviewing the performance of other university departments. So on Wednesday through Friday, I'll be interviewing a bunch of Asian language professors. I'd rather be teaching organic chemistry, but anyway, I do what I have to do. So that means that office hours and class will be disrupted. No class on Wednesday, no office hours Thursday or Friday. I am able to get away to give class on Friday, so we will have class on Friday. Wednesday's lecture will be recorded. We're going to record that this evening, and then we'll post it sometime Tuesday. So you can just watch it at the regular time on Wednesday if you want, but I strongly suggest watching it and not putting that off, because we will have a quiz on Friday since we will be meeting on Friday. So make sure we watch that. And then my office hours tomorrow might be delayed a little bit. I do have a dentist appointment in the morning, and you never get out of those when you want to. So if you show up for office hours at 10, I'll probably be about 15 to 20 minutes after that. All right, and everything will be back to normal next week and should be normal for the rest of the semester. It should only be this week that's a little disrupted. We've talked about reductions of aldehydes and ketones. Today we're going to learn about reductions of carboxylic acid derivatives, a little more complicated than reduction of aldehydes and ketones. We're going to talk about the oxidation of aldehydes. We're actually going to perform one. We're going to have a demo. And then we'll introduce organometallic reagents, or molecules that have carbon metal bonds. So the last topic on regards to reduction of aldehydes and ketones is how these reductions are performed in nature. We showed this slide to you at the end of class on Friday. NADH is the reducing agent in nature. It is a coenzyme. Coenzymes are molecules that function only in the confines of the active site of an enzyme. The part that's in this box here is the reactive portion of the molecule. The remainder of the structure contains functional groups that are able to hydrogen bond or form salt bridges, other sorts of non-covalent interactions with atoms in the active site of the enzyme to be able to hold that coenzyme in the proper location. Okay? This is the full name, but we're always just going to use the abbreviated name for NADH. Here's the mechanism of reduction. So NADH serves as a hydride equivalent, similar to borohydride and aluminum hydride. And we use the lone pair on this nitrogen to expel H-, but H- is not floating around in solution. That would be much too basic to float around in an aqueous solution in a living organism. The enzyme, the active site of the enzyme holds the aldehyde or the ketone very close to the coenzyme, so the H- is able to just hop from one molecule to the other without really being free in the solution. Okay, and then water is present in the active site that can protonate the alkoxide to give us the alcohol. This is done in nature in an enantioselective fashion because the active site is chiral. And it holds the ketone. If it's an aldehyde, of course, it doesn't matter. You get a primary alcohol. But a ketone, if the two R groups on a ketone are different, you're generating a chiral secondary alcohol. And the active site is able to hold the ketone in a position so that just one of its two faces, either the top or the bottom, is going to be exposed to the reducing agent. So as an example, when pyruvic acid is reduced to lactic acid, that's a key step in anaerobic metabolism, anaerobic respiration. Lactic acid is formed as a single enantiomer. I think this is the S enantiomer. And if you're exercising and you need energy faster than you can get from aerobic respiration, this pathway kicks in, and the buildup of lactic acid in your muscles is what causes your muscles to get sore. And then you have to rest once that lactic acid builds up to allow that lactic acid to break down so that you then can exercise again. Okay? Another feature of this reaction is that it is reversible. Okay? NAD plus is the byproduct that is formed after the reduction reaction. If you have a really good memory, hopefully you do, you remember that in chapter 12 of 351M, we learned about NAD plus being used as an oxidizing agent. So the active site of an enzyme, if it has NAD plus, can bind an alcohol, deprotonate that alcohol, eliminate hydride, transfer that hydride to the NAD plus to get the NADH. So you can reverse this whole process, okay? There are driving forces in either direction. When we're performing the reduction, we're generating an aromatic species, right? But it is positively charged. When we go in the other direction, we're losing aromaticity, but we're going from something that's positively charged to something that's neutral. So those two driving forces allow us to perform this reaction in either direction in the active site of an enzyme, depending on the needs of the cell, okay? NADH and NAD plus are derived from niacin, also known as vitamin B3. So you see here, the pyridine ring with the carboxylic acid attached is niacin. And you see where that originates. That's the ring here. And then this amide is derived from the acid. So niacin is present in soybeans. So you eat soybeans, and that helps your body perform these oxidations and reductions. It also is supplemented in breakfast cereal. So if you like to read the labels of breakfast cereals, you'll see niacin or you'll see vitamin B3 on there. Okay. Any questions about biological reductions? Okay, then let's talk about reducing carboxylic acids and their derivatives. There are multiple products that can be obtained from these reductions, and we'll get into that in a minute. And there are two new reducing agents that we're going to introduce that are used with carboxylic acid derivatives. Lithium aluminum hydride, which we learned about previously, is very good at reducing carboxylic acids and their derivatives. And we'll reduce them all the way down to primary alcohols, or in the case of an amide, as we'll learn today, we generate an amine, okay? So these other reducing agents are aluminum-based, okay? This one is referred to as diisobutyl aluminum hydride. It's abbreviated as DIBAL. Note that this is a neutral aluminum compound, but that aluminum hydrogen bond is still polarized towards the hydrogen, so we do have a partial negative charge on this hydrogen. And then our other one, this is lithium tritert-butoxy aluminum hydride. So we've replaced 3 of the hydrogens of lithium aluminum hydride with tert-butoxy groups. Okay. These two species are less reactive than lithium aluminum hydride. Why do you think DIBAL is less reactive than lithium aluminum hydride? Any ideas? What do we think of when we see these? These are isobutyl groups. What does that look like in 3 dimensions? Yes? Exactly. This is bulky, sterically hindered, and so as a result, it is less reactive than lithium aluminum hydride because of the steric hindrance. Okay? You can make the same argument about the tritert-butoxy aluminum hydride, but these tert-butyl groups are further away from the aluminum due to the presence of the oxygen. So there's another reason why this reagent is less reactive than lithium aluminum hydride. Any ideas? Okay, yes, go ahead. Okay, very good. We have a negative charge that's spread out across this whole molecule. And with lithium with aluminum hydride, that negative charge is shared equally by these 4 hydrogens. Over here, oxygen is significantly more electronegative than hydrogen. So the bulk of the negative charge is going to be on these 3 oxygens, and you're going to have less of a negative charge on that hydrogen. You have enough of a partial negative charge on the hydrogen that it does still react and still reduce, but it's going to be less active as a reducing agent than our aluminum hydride. Okay, very good explanation. So we don't have to memorize that these reagents are less reactive than a lithium aluminum hydride. We can understand it by looking at the structures. However, all of these are more reactive than sodium borohydride, which we learned about last week, due to the lower electronegativity of aluminum than boron. Okay? So when we're reducing carboxylic acid derivatives, there are different outcomes, different possible outcomes of the reaction depending on the nature of the reducing agent. So if we take an acid chloride and we react that acid chloride with lithium aluminum hydride, followed by the addition of water, remember we have to do that in 2 different steps, we're going to get the primary alcohol. We get a lithium chloride byproduct as well, but we're not going to draw the inorganic byproduct. Okay? However, if we use lithium tritert butoxy aluminum hydride or Dibol, these 2 reagents are interchangeable. So when we can use one, we can always use the other. So I just randomly chose tritert butoxy aluminum hydride. We could have chosen Dibol. Okay? The book doesn't tell you this, but you need to perform this reaction at a very low temperature. And I'll explain why in a moment. It's a critical part of this reduction. And then you're adding water. In this case, you're going to generate the aldehyde. Okay? So we're not reducing it all the way to the primary alcohol. We're stopping at the aldehyde. Okay? The same thing applies to esters. Let's just raise this up just a little bit. If we have an ester that we're reducing, and we reduce that ester with lithium aluminum hydride, followed by the addition of water, we're going to get the alcohol just like above. In this case, methoxide is our leaving group. When we protonate that, we generate methanol. So we actually get 2 alcohols in this reaction. In most cases, when you reduce esters, it's the longer chain alcohol that you desire. And you can separate these 2. They'll have different boiling points. So that's not a big issue. If we take one of our other aluminum reducing agents, either Dibol or lithium tritert butoxy aluminum hydride, remember these are interchangeable. We run that reaction at low temperature. We add water. Now we're going to get the aldehyde as our product. And methanol is a byproduct. Of course, the polarity of these 2 species is going to be significantly different, so we would be able to separate them. Okay? So we need to look at the mechanism of this reaction to understand why we get alcohols in one case and aldehydes in the other case. Let's look at it on the screen because the mechanism has much in common with both the general mechanisms we learned last week as well as the specific mechanism of aldehyde and ketone reduction. All right, so Z here can be a chlorine or an alkoxy group, so this mechanism is the same for reducing acid chlorides and esters. And the first step of the reduction is going to be the same as it was with reducing aldehydes and ketones. And if this is not aluminum hydride, then you just have one of these aluminum hydrogen bonds, and you have other things attached, either these isobutyl groups or these tert-butoxy groups. But the mechanism of the step is the same regardless. Okay. So you attack the carbonyl carbon, you generate this tetrahedral intermediate. We've seen that before. What's different from reductions of aldehydes and ketones is that we now have this Z group that is a leaving group. So we eliminate Z, reforming our carbonyl, generating our aldehyde, and then we have our leaving group. In the case of an acid chloride, that leaving group is a chloride ion. That's something we're comfortable with, something we're used to seeing as a leaving group from 351M. If this is an ester, it's an alkoxy group. If it's a methyl ester, like we drew on the board, it would be methoxide. Methoxide is a strong base, too strong of a base to be used as a leaving group in SN2 reactions. So why can we use it as a leaving group here? The reason is that even though it's basic, it's less basic than our reducing agent that we started with. Okay, this is a stronger base than methoxide. And so over these two steps, we're converting a stronger base into a weaker base. So it works because our reducing agents are much stronger bases than our nucleophiles were in 351M. We can now accommodate poorer leaving groups in these reactions than what we've done before. Okay, so that's how we get to the aldehyde. Now, part two is simply reduction of the aldehyde to the primary alcohol by the two steps we learned on Friday. Another equivalent of aluminum hydride attacks, generating the alkoxide. We then add water at the end, protonating that alkoxide, giving us our product. Okay, so a couple of things about this. One is, if you notice this mechanism, you'll see that we're using two equivalents of the aluminum hydride. If you look at the book is not very good about specifying two equivalents. And that's because we can actually do these reductions with one equivalent of lithium aluminum hydride, because ALH3 has aluminum hydrogen bonds with partial negative charges on the hydrogen. And so this byproduct can also do this reduction. Okay, so even though the mechanism would suggest we need two equivalents of lithium aluminum hydride, we don't actually. So either way, sometimes we use two equivalents just to speed it up, but we don't have to, okay? Because this byproduct is also capable of reducing the aldehyde that is formed, okay? All right, then the second thing that you might have noticed is we're producing an aldehyde from an acid chloride or a ketone. And aldehydes are more electrophilic. They're more reactive than acid chlorides or esters are. The acid chloride and the ester have that heteroatom with a lone pair that donates electrons to the carbonyl carbon. And so the aldehyde is significantly more electrophilic than the ester or the acid chloride. So you produce the aldehyde. Let's say you're using one of these reagents, dibal or lithium tritert-butoxy aluminum hydride, and you're trying to make the aldehyde. Let's say the reaction has gone to 50% completion. When it's gone to 50% completion, we're going to have a one-to-one mixture of aldehyde and ester, or acid chloride, and we're still going to have 50% of our reducing agent remaining. What is our reducing agent going to react faster with, the aldehyde or the ester? The aldehyde. So as soon as that aldehyde builds up, it's going to get consumed much faster than the starting ester. So you're not going to be able to stop at the aldehyde. It's going to go all the way to the primary alcohol. If you use one equivalent of these reducing agents, you're going to get a mixture of primary alcohol and unreacted ester. You're not going to have any aldehyde in there. Okay. So was I lying? How did we stop at the aldehyde? The answer is right here, the minus 78 degrees, the low temperature. And if you're wondering why we use this odd temperature, it's because that is the temperature of a mixture of dry ice and acetone, two very convenient and common materials. So you just plunk dry ice into acetone, it bubbles a bit. Once it stops bubbling, it's minus 78 degrees. So it's a very convenient low temperature in the lab. At minus 78 degrees, step 2 of part 1 does not happen. At that low temperature, we are not eliminating that leaving group. We are not forming the aldehyde. So what that allows us to do is to run step 1 without performing step 2. That allows us to completely consume our 1 equivalent of reducing agent before we generate the aldehyde. So that reducing agent never sees the aldehyde because we consume it all in step 1 before we take away our dry ice acetone bath, allow it to warm up to room temperature, and then we spit out our leaving group and get the aldehyde. So that is why the minus 78 degrees is critical. It allows us to perform step 1 without performing step 2, because step 2 won't occur at that low temperature. And so then we do not form the aldehyde until we've consumed our 1 equivalent of the reducing agent. Okay? So you might wonder, why can't you just do this with lithium aluminum hydride? The problem is the byproduct you get in lithium aluminum hydride will react with the aldehyde. So when you warm it up, when you take away that cooling bath, this will reduce that. Okay? So it only works with our dibol or our tritert-butoxy aluminum hydride. Okay? Any questions about how we can obtain aldehydes from esters and acid chlorides? So minus 78 is key. That's not in the book. So make sure you've got good notes on that and make sure you understand why we have to perform the reaction at the low temperature. This chemistry is widely used in labs. Here's an interesting example. Ciguatoxin is what's known as a ladder polyether. We learned about brevetoxin last semester, which is a relative of ciguatoxin. These molecules are produced by organisms that cause red tides that kill off shellfish and marine life. They're long molecules. They're rigid molecules. They have oxygens capable of hydrogen bonding. So it shouldn't surprise you that these can insert themselves into cell membranes and create artificial ion channels, much in the way that amphotericin B does, which we learned about last semester. So some chemists who wanted to study these molecules, they weren't trying to poison people, they were just trying to learn more about how they work, synthesized this compound. And a key step in their synthesis was reducing the ester to the aldehyde. And of course, they used minus 78 degrees. That was just glossed over in our textbook. And that allowed them to get the aldehyde, which is a key intermediate. Okay? All right, so let's talk about, so these are 2 of our carboxylic acid derivatives, the acid chloride and the ester. What about reductions of carboxylic acids and amides? Those reductions are complicated by acid-base chemistry. We know that our carboxylic acid is acidic. So if we react that with anything that's got a metal hydride bond, we're going to deprotonate the carboxylic acid. We're going to form hydrogen gas, a very stable byproduct. And we're going to get a carboxylate salt. Okay? This carboxylate salt has a negative charge on the oxygen. It's not going to be very electrophilic with that negative charge. So it's going to be very hard to reduce. So only our strongest reducing agent, the lithium aluminum hydride, is going to be able to reduce our carboxylic acids. Lithium aluminum hydride reduces anything. It's the nuclear bomb of reducing agents. It'll take out anything in its path. And so it will reduce this carboxylate, even though it is negatively charged. Okay? The same thing can happen with amides. The NH of an amide is also acidic enough that it can be deprotonated. Another problem we face with amides is this minor contributor becoming more prominent due to the lower electronegativity of nitrogen than oxygen. So we have more electron donation from the nitrogen of an amide than we do from the oxygen of a carboxylic acid or any of its other derivatives. And so that decreases the electrophilicity of the carbonyl carbon of an amide, meaning that with amides as well, only lithium aluminum hydride will reduce it. Okay? So if we reduce a carboxylic acid, we're going to get a primary alcohol, much like we would if we reduced an ester or an acid chloride using lithium aluminum hydride. We'll get primary alcohols from those reactions. But if we reduce an amide, the result is different. We generate an amine. And this happens with any type of amide. A primary amide is one where we have NH2. A secondary amide would be one where we've replaced one of our hydrogens with some kind of alkyl or aryl group. Okay? And then a tertiary amide would be one where we have no NH, where we only have alkyl or aryl groups attached to the nitrogen. But any of these types of amides, we're going to react with lithium aluminum hydride, and we're going to add water in a second step, and we're going to obtain an amine. Okay? So instead of obtaining an alcohol, we obtain an amine from this reaction. Okay? We're going to draw a mechanism for this to understand why this happens. But the short explanation is that our nitrogen is going to be a terrible leaving group. A negatively charged nitrogen is very strong as a base, too strong as a base to function as a leaving group. So we're going to have to keep that on our molecule and have something else function as our leaving group in this reduction. Okay? So we'll draw a mechanism. This mechanism will also serve as the mechanism for carboxylic acid reduction. You would just replace the nitrogen with an OH, and you could draw the same kind of mechanism. So that's something you should do on your own to make sure you understand the mechanism of carboxylic acid reduction. Okay? So, drawing the reduction of an amide. This will work for primary amides with NH2, secondary amides that have one NH. The mechanism is different for tertiary amides. It's more complicated, so we're not going to learn it. We'll just have to trust that if we use a tertiary amide, it will be reduced by a related but slightly different mechanism to still generate amines. But the first thing that's going to happen here, I'm just going to write our aluminum hydride in this fashion, is acid-base chemistry. Our basic aluminum hydride species is going to deprotonate our NH, our acidic NH. That's going to give us hydrogen gas. Again, a very stable byproduct. It's going to give us this anion. Now, this is an allylic anion. It has a resonance structure. We could have drawn the carbon-oxygen double bond and the negative charge on nitrogen. Why did I draw it this way? Why did I draw this resonance structure instead of the other one? Something about which atom bears the negative charge? Does that jog some memories? Yes, Grace? Yes. So we know that having the negative charge on the more electronegative atom is going to be more stable. And so the resonance, if we had drawn this arrow just to the nitrogen and put the negative charge on the nitrogen and kept our carbon-oxygen double bond, that would be higher in energy because the negative charge would be on a less electronegative atom. Okay? So we get to this species. The negative charge on oxygen is more stable than on nitrogen, but it is still basic. Lewis basic, Bronsted basic. We've also produced ALH3 as a byproduct in this reaction. This aluminum is neutral, but it doesn't have the octet. So this is a really, really good Lewis acid. So what happens now is our oxygen attacks there. We generate a Lewis acid, Lewis base complex. Okay, that's going to have the negative charge on the aluminum now. Okay. Okay. All right, we have a carbon-nitrogen double bond. That's known as an imine. It's comparable to a carbonyl. Nitrogen is less electronegative than oxygen, but this bond is still polarized towards the nitrogen. We have a partial positive charge on that carbon. So that means that another equivalent of our aluminum hydride is able to attack. And we can push the electrons onto the nitrogen. Okay. So we have a tetrahedral intermediate looking like this. It's a dianion, but those negative charges are spread out. They're fairly far apart from each other, so that's okay. So our tetrahedral intermediate is going to now collapse and eliminate out a leaving group. It turns out that this species is a much better leaving group than this one, because the oxygen being more electronegative than the nitrogen, more likely to bear a negative charge. Okay. So this intermediate is known as an imine. And then our leaving group, it should be painful to look at this leaving group because we've drawn a species that has negative charges on adjacent atoms. Okay, that should hurt your eyes. We usually don't see anything like that. That would be you'd think that would be unstable. But this is not that unstable. Okay, why not? Where is the negative charge that I've drawn on the aluminum actually located? It's on the hydrogens, yeah. So it's removed from that oxygen. It's spread out across those three other hydrogens. So this is not as unstable as you might think. In fact, it's a better leaving group than this would be, right? NH with two negative charges would be a much worse leaving group than this thing. So when given a choice, this is the better leaving group, okay? All right, so we get to the imine. That's going to react with another equivalent of our aluminum hydride. Okay. Giving us a tetrahedral intermediate. There's a negative charge on that aluminum hydride I forgot to draw. And I'm going to move this plus so that it doesn't look like it's attached to the molecule there. Now we've reached a tetrahedral intermediate with no leaving groups attached. And so now is where we add our water to generate the final product. Okay? So we protonate. We have hydroxide as a byproduct. Okay? And that's how we get primary amines. If we were reducing acids, we just replace this NH unit with an oxygen and do all the same steps. Okay? Any questions about the reduction of amines, or I'm sorry, the reduction of amides to generate amines using lithium aluminum hydride? Okay, so we've talked about a fair number of reductions. Here we have a summary of those reducing agents. And we should not have to memorize this table because we have explained why sodium borohydride is the weakest of our reducing agents. Boron is more electronegative than aluminum. And we've explained why lithium tritert-butoxy aluminum hydride and dibol are weaker reducing agents than lithium aluminum hydride. So we should understand the hierarchy of reactivity. We should understand that sodium borohydride is only reactive enough to reduce aldehydes and ketones and not reactive enough to reduce carboxylic acid derivatives, okay? And then we should understand why, at low temperatures, at minus 78, these two reagents will give us aldehydes, whereas lithium aluminum hydride will generate primary alcohols in all cases. Okay? And then lithium aluminum hydride is the one that will generate amines. It's the one that's strong enough to reduce those negatively charged species that we generate by the acid-base chemistry with either a carboxylic acid, which is shown here, or an amide. Okay? It's not shown here. These two reagents would also reduce aldehydes or ketones. Okay? They haven't shown it, but these would work perfectly fine to reduce aldehydes or ketones. They would also work fine to generate primary alcohols if you were running the reactions at room temperature or 0 degrees and using two equivalents. Okay? Any questions about the information in this table? Okay, yes, question. Okay, that's a great question. You'd think that it would be. The problem is when you use lithium aluminum hydride, we have this byproduct, and that byproduct reduces aldehydes. So you're going to have this in here when you get to step 2, and as soon as you form that aldehyde, it's going to get reduced. So because you have this ALH3 byproduct that you don't have, you'll notice these other reagents, which are now way at the top of the board here, only have one hydrogen on the aluminum. So we can get rid of that in step 1. But we're not getting rid of that with aluminum hydride in step 1. Even at that temperature? Well, because you're eventually going to have to generate the aldehyde. You're going to have to warm it up. And when you do, this is going to be sitting there. And so you cannot stop at the aldehyde with lithium aluminum hydride. All right, let's talk briefly about oxidations. So the only carboxylic acid, or the only carbonyl compound, that we're going to oxidize is the aldehyde. We can oxidize aldehydes to carboxylic acids. We can use any of the, other than PCC, we can use any of the other chromium reagents we learned about in chapter 12. Chromium trioxide, dichromate, we use those in the presence of acid. Those can oxidize aldehydes to, carboxylic acids. But the problem is if you have alcohols present in your molecule. So let's say you have a molecule that looks like this, has an OH group and an aldehyde, and you want to oxidize just the aldehyde. You want to keep the alcohol. You don't want to oxidize that. Well, you'd be out of luck if you were using chromium trioxide or dichromate or any of those reagents. You'd need something else to oxidize only the aldehyde. And that something else is silver oxide with ammonium hydroxide. Okay? This combination is known as the Tollens reagent. Okay? So the Tollens reagent will oxidize aldehydes to carboxylic acids. The mechanism is one of those complicated oxidation mechanisms that we're not going to learn. So in this case, we actually just have to memorize the reagents. One thing that is memorable about this reaction is that silver is produced as a byproduct, and silver is metallic. Silver forms a mirror. So you generate a silver mirror when you do this reaction. Okay? So we're going to perform this reaction today. It goes faster at warmer temperatures. So what we've been doing during the class is just warming up some water in this flask so that the flask is going to be warm when we add the reagents. Okay? So we'll dump out our warm water. Okay, that's still, we're going to add our reagents here. Okay. All right, and then I think this is where our alcohol is. We're going to add this in. And then we're going to cap it. And you see we formed silver. We're going to shake it up really good, and that silver is going to coat the flask. Okay, and hopefully you can see yourself. I can see myself in the back end of this. We've made a silver mirror due to the silver byproduct that we've formed. So this silver mirror is proof that we've been able to oxidize the aldehyde that was in here to a carboxylic acid. Okay, any questions? Yes. That's a good question. It depends on what those Reddit investors are doing to the price of silver, I guess. So I can't answer that question, but that's a good question. You sound like my son, always trying to come up with some sort of get-rich-quick scheme. But no, the lecture prep guys are going to clean this off, and when they clean it off and use acid, I don't think it's going to be metal silver anymore. So sorry to disappoint. All right, so that's our oxidation. We're not going to learn the mechanism, but hopefully we'll remember it involves silver because we've seen the silver form in this reaction. Okay, so in our remaining time, we're going to talk about organometallic reagents. These are molecules that have a carbon-metal bond. Okay, so it'll look something like this. And regardless of what metal we're using, that bond is going to be polarized towards the metal. Or sorry, I drew that backwards. Polarized towards the carbon. So that means we have a partial negative charge on the carbon and a partial positive charge on the metal, because the carbon's always more electronegative than the metal. So because we have a partial negative charge on carbon in these molecules, they react as equivalents of carbanions. Okay, this would be a carbanion with a full negative charge on the metal. Right, we don't have that, but we have a high enough partial negative charge that these species are going to react as if they were carbanions. And so they're going to be very strong nucleophiles, and they're going to be strong nucleophiles capable of forming carbon-carbon bonds. So that'll be very useful for us. There are many types of organometallics, but there are three common ones that we're going to learn in this chapter. The organolithium reagent, the organomagnesium reagent, which is also known as a Grignard reagent. And because magnesium is a divalent cation, we need a halogen, usually a chlorine or a bromine, but could also be an iodine, in our Grignard reagent. And then we have a funny looking one, which has two R groups, a negative charge on a copper and a positive charge on a lithium. That's known as an organocuprate. Okay? So we're going to look at electronegativity values for the metals that are bonded to the carbon in these species. Lithium, it's 1.0. Magnesium, less electronegative than lithium, 1.3. Copper, less electronegative than magnesium, 1.8. So based on these values, which of these organometallics do you think is going to be the most reactive? Okay, which one? Okay, the organolithium will be the most reactive. Carbon's electronegativity is 2.5. I didn't write that up there. But we're going to have the biggest electronegativity difference with lithium in the organolithium reagent. Okay, so this is most reactive. The organocuprate is the least reactive. For practical purposes, especially for the reactions we are learning in class, the difference between the organolithium and the organomagnesium reagents is negligible. So these two reagents are going to react the same in all the reactions we're learning in class. Okay, this difference is not going to be enough to cause them to behave differently from each other. Okay. However, the difference between magnesium and copper in terms of electronegativity is significant enough that the organocuprates are going to have different reactivity from our other two. Okay, so lithium and magnesium reagents will react the same. Organocuprates will react differently. So briefly, we'll talk about how these are made. They're made from alkyl halides. If we add 2 equivalents of lithium to an alkyl halide, we will get an organolithium, and then we have a lithium halide salt byproduct, okay? We're not going to go over the mechanism of this. It's going to involve radicals and single electron transfers. So it's not something we're going to go over. The important thing to note is that we can generate an organolithium in one step from an alkyl halide, okay? Another thing I'll mention to you is that our organometallic species do not have to be just alkyl groups. We can have aryl organometallics. We can have vinyl organometallics. We can have alkynyl organometallics. We can have organometallics of any type. Okay, so it doesn't just have to be an alkyl halide. Okay. So our Grignard reagents, or the organomagnesiums, here we just add magnesium. We usually do this with ether as a solvent. That's diethyl ether. Also involving single electron transfer, that magnesium is going to insert itself between the carbon and the bromine. And because our metals are very good Lewis acids, when we use these Lewis basic solvents, we have these Lewis acid, Lewis base interactions. Sometimes we use arrows to show that our solvents are going to form Lewis acid, Lewis base interactions that stabilize our organomagnesiums, or our Grignard reagents, in the solution. So again, the key thing here is just noting that these come from alkyl, aryl, vinyl, alkynyl halides, and not necessarily knowing the mechanisms of these processes. The organocuprates have to originate from the organolithiums, and you need 2 equivalents of your organolithium and copper iodide, and that's going to give you, our organocuprate, and then you're going to have a lithium iodide byproduct. Okay, so 2 steps to generate our organocuprate species. Now there's an organometallic that we learned about earlier in the class, back in chapter 11, that we used to form carbon-carbon bonds. Does anybody remember what it was called? Think back to chapter 11. Think back to how we make carbon-carbon bonds. Minnie? Acetylides, yeah. So we made sodium acetylides. We took terminal alkynes. We reacted them with sodium amide, NaNH2. We deprotonated. Maybe I should go ahead and draw the mechanism out here. So let me draw our NaNH2 like this. Okay. And then we had ammonia as a byproduct. So sodium acetylides, we didn't draw with a covalent bond, we drew them as a salt. That's because sodium is less electronegative than lithium. And so the sodium carbon bond is in the range where it would be considered ionic. Okay. We can also make lithium acetylides. We can take, and this is an alternative way that works just for alkynes. It doesn't work for other types of organometallics, but because terminal alkynes are more acidic than other types of hydrocarbons, we can take an organolithium such as methyl lithium. This methyl lithium is a strong base. I'll show you why in a minute. We can deprotonate this, and that's going to generate, we'll go ahead and push this electron here, but we're going to draw the species with a covalent bond between the carbon and the lithium as opposed to an ionic bond in this case. And what's our conjugate acid of methyl lithium? I've drawn it for you here. What's the conjugate acid of this? Think back to chapter 2. Got to remember our acid-base chemistry. So this is our acid, this is our base. You protonate the base, you get the conjugate acid. Methane, is methane a very strong acid? Not at all. It's incredibly weak. pKa of methane is 50. The pKa of a terminal alkyne is 25. Right, so this is a favorable process. This is another way of making acetylides. This lithium acetylide is covalent as opposed to our ionic sodium acetylide, but the reactivity is close enough that this will still react with all the same things that we saw sodium acetylides reacting with in chapter 11. And this reaction points out something about organometallics, which is that they are quite strong bases. Their conjugate acids are either alkanes or alkenes or aromatic rings, depending on what kind of group you have. So if you take methyl lithium and you expose it to water, you're going to have an acid-base reaction. You're going to generate methane gas and lithium hydroxide. Okay. All right. That's a pretty expensive way of making lithium hydroxide because you went to a lot of effort to making your methyl lithium. So this is usually not something that you want to do. So what this means is that you have to keep your organometallics away from water. You have to keep them away from alcohols. You have to keep them away from amides, carboxylic acids. You have to keep them away from molecules that have readily, fairly acidic hydrogens. Okay? There is one case in which the acid-base or the basicity of the organometallics is useful, and we'll talk about that at the beginning of our recorded lecture that you can watch either tomorrow or Wednesday. So I'll see you on Friday or at my office hours tomorrow or Wednesday.